So we are back again. So this is now all this just 1 minute, that all these nomenclature are given below, right. So given below. So this is your mutual inductance of F1 of coil 2. So see the meaning of this now, your suffix, right. So this way you can you can find out what will be the mutual inductance, right. So L1 is the self inductance of coil 1, everything is given, all nomenclature is given. L2 is self inductance of coil 2, N1 number of turns of coil 1 given, N2 number of turns coil 2 is given. Phi 1 is magnetic flux emanating from coil 1, and phi 1 one component of phi 1 links coil 1, I told you, and phi 1 2 another component of phi 1 links both coil 1 and coil 2, that I also told you. So hence phi 1 is equal to phi 1 plus phi 1 2, right, the total flux. Now although the two coils are physically separated, they are said to be magnetically coupled, right, because flux part of the flux is linking also the other coil. Since the entire flux phi 1 links coil 1, the voltage induced in coil 1 will be V1 is equal to N1 into d phi 1 upon dt, because phi 1 is equal to phi 1 plus phi 1 2. So whole phi 1 linking the coil 1. So voltage V1 induced in coil 1 will be N1 into d phi 1 upon dt, or only flux phi 1 2 links coil 2. So the voltage induced in coil 2 will be V2 will be N2 into d phi 1 2 upon dt. This diagram V2 will be your, this number of turns is N2 into d phi 1 2 upon dt, because phi 1 2 links the coil 2, right. So that is V2 is equal to N2 d phi 1 2 upon dt. Now again, as the fluxes are caused by the current I1 flowing in coil 1, we can write for V1 we can write, because flux phi 1 is caused by your current I1, because your coil 2 no current source is connected. So V1 is equal to, we can write the again chain rule, N1 into d phi 1 upon di1 into di1 upon dt. This you can write L1 into di1 upon dt. So that means L1 is equal to actually N1 d phi 1 upon di1. It is actually self inductance of coil 1, right. This is self inductance of coil 1. Now similarly for V2 case we can write again chain rule, V2 is equal to N2 d phi 1 2 upon di1 into di1 upon dt. This actually, it is actually mutual inductance. So N2 d phi 1 2 upon dy1, we are writing M21 di1 upon dt, where M21 is equal to N2 or what you call N2 into d phi 1 2 upon di1. This is actually mutual inductance, right. So M21 mutual inductance of coil 2 with respect to coil 1. This is the meaning of the suffix, right. So that here, that's why I have written for you. Subscript 21 indicates the inductance M21 relates the voltage induced in coil 2 to the current in coil 1. This is the meaning, right. So there should not be any confusion, right. So thus the open circuit mutual voltage or induced voltage, right, across coil 2 will be V2 is equal to M21 di1 upon dt, because flux I1 actually creating your current I1 actually creating the flux I1, and part of the flux linking the your coil 2, therefore V2 will be M21 di1 upon dt, that here it is, right. So V2 is equal to M21 di1 upon dt. This is the your induced voltage, right, due to the flux linking the other coil. So now similarly, if you this side if you suppose excited by current I2, and this side it is your V1 L1 L2, this down here also phi 2 is equal to, phi 2 is the total flux, same as before, phi 2 is the total flux is equal to phi 2 2 plus phi 2 1. So part of the flux, your what you call part of the flux of your phi 2 actually linking the this coil 1, right, and this is we are calling phi 2 1, but this phi 2 is equal to phi 2 2 and phi 2 1, then both, but this is the total flux. So this phi 2 2 and phi 2 1 both linking coil 2, and this is the voltage V2, this is V1, same as before. This is mutual inductance M12 of coil 1 with respect to coil 2, right. So that will be phi 2 is equal to phi 2 1 plus phi 2 2, same as before. V2 will be coil 2 number of turns N2 d phi 2 upon dt. that is N2 d phi 2 upon di2 into di2 upon dt, chain rule. So, this is L2 into di2 upon dt, right. So, L2 is the self inductance of the coil 2, meaning is same, right. And V1, that is the induced voltage due to that flux linking your what you call in coil 1 due to the current in your coil 2. So, V1 is equal to N1 d phi 2 1 upon dt is equal to N1 d phi 2 1 upon di2 into di2 by dt. This is again chain rule. So, this part is called your M12, that is di2 upon dt. Therefore, V1 is equal to M12 di2 upon dt, right. But M12 and M21 are equal, that is M12 is equal to M21 is equal to M. It cannot be different, right, this way or that way, mutual inductance has to be same, right. So, M is actually M12 is equal to M21, right. So, this is your equation number, I did not put, just make step by step, it is understandable to you, right. Now something I have written, keep in mind that mutual coupling only exists when the inductors or coils are in close proximity and the circuits are driven by time varying sources. So, this is I have written for you. Recall that inductors act like short circuit to DC, right. So, that is why this is written for you, that keep in mind that, right, mutual coupling only exists when the inductors or coils are in close proximity and the circuits are driven by time varying sources. Now, the polarity of mutual voltage, this is the only thing we have to see, the polarity of mutual voltage, whether it will plus or minus M di by dt is not easy to determine, because 4 terminals are involved, right, because your what you call that in the coil 1 side plus minus voltage terminal and in the what you call in the coil 2 side also plus minus. So, 4 terminals are involved, right. The choice of the correct polarity for M di by dt is made by examining the orientation or particular way in which both coils are physically wound, right, and applying Lenz's law in conjunction with the right hand rule. This is a difficult one, right, but for our circuit analysis what we will do, we will apply the dot convention in circuit analysis. In our magnetic circuit analysis or this thing we will apply the dot convention, right. So, by this convention a dot is placed in the circuit at one end of each of the 2 magnetically coils to indicate the direction of the magnetic flux if current enters the dotted terminal of the coil, right. Now, question is, suppose this is your what you call, we will use dot convention, suppose this is dot is here, right. Let us try to understand this. Suppose a dot is here, here we have make the dot, and here also dot is there, here also dot is there, here also dot is there, right, and your illustration of dot convention, coils are wound here, right, coils are wound here. Now, question is, this current I1 is direction and I2 is in direction, right, in this direction. Now, question is that how to we take plus or minus. Now, question is that this is that current entering. Now, you grasp the your what you call, you grasp the your coil, right. So, in the direction of the current you grasp it, right, just you curl it right this, and this way this is that your what you call, this is the flux actually, this direction of the flux, this is the direction of the flux. So, for this coil 1 actually phi 1 is equal to phi 1 1 plus phi 1 2, because this is the direction, ultimately this is the direction it is taking, right. You grasp in the direction of the current, that your what you call in the direction of the current, that where this coil is this direction of the current and this coil is owned. So, you grasp it, and this is in the direction of the current, you grasp the coil, and this is in the direction of the current, and thumb will indicate your direction of the flux. So, this is coming out flux. So, this is phi 1 2 and this is also coming out from this. So, moving like this, because it is linking the coil 1 phi 1 1 and part of this is coming here and linking your the coil 2. Similarly, this side also current is entering, say I2, a dot I have placed like this, right. So, phi 2 is equal to phi 2 1 plus phi 2 2. Here also if you make like this, that current is moving in this direction, and you grasp the your what you coil in the direction of the current, and this finger is showing like this, it is coming to the bottom of this your what you call the bottom of this side, right, in this figure. That means flux is your what you call coming out from this is coming out for this, that is why this is the thing, and that is why this way this is the direction of the flux. So, this is actually phi 2 phi 1 2 and phi 2 1 both are in the same direction, that is additive, isn't it. So, but this phi 2 1 actually linking this coil, and all the phi 2 1 and your what you call phi 2 is equal to your phi 2 2 and plus phi 2 1, all this linking coil 2. So, this way you have to understand the dot convention, right. So, if it is so, this is illustration of dot convention, that how we will do it, right. So, let me clear it. So, hope this direction of the flux, that how things are coming, you have understood. What is there? Just look at the coil, see the direction of the current, it grabs the coil in the direction of the current, and direction of the your thumb will be the direction of the flux, right. And this side voltage is V 1 and this side voltage is V 2. Hope you have understood this, right. So, this way dots are used to determine the polarity of the mutual voltage using this dot. Now, question is that suppose dot convention is stated as follows: if a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is positive at the dotted terminal of the second coil. This is the language I have written, that we will come to that figure and other thing. If a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage, right, in the second coil is positive at the dotted terminal of the second coil. So, alternatively, if a current leaves the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is negative at the dotted terminal of the second coil, right. For now, if we come to this, right, suppose this your what you call this current, your what you call in figure 10, the two coils are there, dots are shown, these dots are shown. Here current I 1 is entering and mutual inductance between this coil is shown by M, here it is M, the mutual inductance, and this is coil 2 simply written M into d I 1 by dt, because current is I 1 and mutual voltage induced in this, it will M into d I 1 by dt. This is the mutual inductance. We are not writing M 1 2 or M 2 1, M 1 2 is equal to M 2 1 is equal to M. Now, in figure 10, the sign of the mutual voltage V 2 is determined by the reference polarity for V 2 and direction of I 1, right. So, in this case current is entering in the what you call, this is the reference polarity is given, that is your plus, right, and current entering into your dot, right, and this is the reference polarity. So, and dot is marked here in the reference polarity plus. So, this is actually V 2 is equal to M into d I 1 upon dt, right. So, it is actually plus sign M d I upon dt. Next is, so here it is, that is why written determined by the reference polarity for V 2 and direction of I 1. Now, similarly, now that is I 1 enters the dotted terminal of coil 1. So, I 1 actually entering into the dot. So, this I 1 actually is entering into the dotted terminal, right. Much more we will see. So, and V 2 is the positive at the dotted terminal of coil 2. Therefore, mutual voltage is plus M d I 1 upon dt. Now, this is our reference polarity we have taken, this is reference polarity we have taken plus. So, dot actually it is that reference polarity plus we have taken, and dot is also the reference polarity plus. So, that is why this V 2 is equal to M d I upon dt. That is why it is written that your what you call that V 2 is positive at the dotted terminal of coil 2, right. So, mutual voltage is plus M d I 1 upon dt. So, I 1 entering the dotted terminal of coil 1 and V 2 is positive at the dotted terminal of coil 2, right. Now, mutual voltage is plus then M d I upon dt. Now, next one is that second diagram. So, dot is here and dot is here, suppose it is marked. So, current is entering into this dot, right, but in this case the reference polarity here it is minus, dot is, this dot is placed to the reference polarity is minus. So, V 2 will be minus M into d I 1 upon dt. This is that the current, although current is entering into the dot, but dot is here, a reference polarity for V 2 that is here, this minus. So, it will be minus M d I 1 upon dt. When both are your both sides current are injected, we will see later, right. Now, similarly other way also, now this side that current I 2 is your what you call current I 2 is your entering here, but leaving the dot. Here if you look into that this is current I 2 actually leaving the dot, right. But question is that the reference polarity here, this is your what you call, this is your reference polarity here it is plus and here it is your plus, but current leaving the dot, that is why here it is minus. because you have to see here current actually leaving the dot, right. So that means it is your what you call, it is your minus, right. So another thing is that that's why it is minus m di2 by dt, because current here is I2, but here current is, if you put the current is dot is here, by chance if you put, suppose if you put dot is here, right, then it will be plus m di2 by dt, but question is that current here your what you call leaving the dot, it is leaving the dot, you have to see the entering the dot or leaving the dot. But reference polarity, although this side is plus 1, but current is leaving the dot, so it is minus m di2 upon dt, right. Similarly, if you see here, in this case, if you see here current actually this I2 leaving the dot, and dot is here in this minus also, the reference polarity is also minus, and current leaving the dot, that means this will be plus, right. So idea is, how you remember, I will tell you one different rule. For example, suppose this is plus minus, this you mark plus minus, right. So question is that if both dots are here, it will be plus. If either of these, either it is here or here, or it is here or here, so it is plus, your plus into plus is equal to your plus, right. So it is like this. So if it is either is here or is here, it is plus into minus, so it will be minus sign, right. And if it is minus 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 minus, it will be plus sign. So that's why it is plus sign. This way you can easily remember, right. So this is one, this rule will not tell you anywhere, right. This is just to, if you want to keep it in your mind, then you will find things are very simple, right. You see both dot, I mean this kind of thing, here it is minus, here it is minus, right. Here current leave the terminal, and reference dot is this one, it is coming plus, right. Similarly, if you look here, here it is your what you call, here it is plus, and here you mark plus minus, here it is plus, here it is minus, so plus minus minus, right. Similarly, if you put the dot is here and dot is here, so plus minus, it will be your, again it will be your what you call, it will be minus, right. So this way you can remember, right. Similarly, if you come to previous your other two figure, here if you look, this is your, if you mark this one, this is my plus, this is plus minus, so plus minus, look, minus has come. If you reverse the dot this way also, if it is like this, then it is also, it will become your what you call, it will be minus, right. So let me clear it. Same is for the figure 1. So same is for your this figure 1. This is plus. If you mark this one, the current is entering, you mark this one as a plus, and this is minus, so plus plus, so it is plus. So this way you can write plus plus plus, minus minus plus, plus minus minus, minus plus minus. This way you can do it. So easy to remember, right. So with this, that how to get the sign, right. So dot convention. Now this one, now next one we will take, this is your L1 L2, that inductance of coil, self inductance of coil L1 L2, and mutual inductance M is given. This side current is I1, this side current is I2. So in this case what will happen, that both the cases current is here, but look into that, the convention is current is entering into the dot, and this current also entering into the dot, both the currents entering into the dot, that means sign will be plus. That is why V1 if you write, it will be L1 di1 upon dt, right, plus m di2 by dt. This is V1. So this is for your V1, you write L1 di1 upon dt, it is written there, but due to this I2, that some your voltage will be induced in the coil, your what you call coil 1. So that is the mutual inductance M into di2 upon dt. Similarly, for V2 will be L2 di2 by dt plus M, right, then your what you call into di1 upon dt into di upon dt. This together, this is now equation 1. So this way you can write. Now if you either of this dot, if it is change after some if you put some, this dot is here, or let me clear it, or this dot is here, this will be there, then in that case your what will happen, the sign will change, the same sign will change, right. For example, if this your this dot is here, suppose this is not there, so it will be minus, I told you, plus minus minus, right, something like this, right, because current actually leaving this dot. If dot is here means this current is entering and another is leaving, you have to take the minus sign. In that case it will be your what you call minus. See, here also it will be minus, so it will be now plus minus, right, plus minus. So that's why reversing the dots or reversing the assumed direction of current, right, or voltages in either winding will change the sign of mutual your terms in equation 1. Even either of the I told you, either you dot or you can reverse the, you have to see the current is leaving, right, the dot. For example, if you just instead of this direction, suppose current direction is like this. So that means what? It is, this is the current leaving the dot, right, and it is entering the dot, it will be minus, right. You have to see, if both current enters the dot, it will be plus sign. If both current leaves the dot, then also it will be plus sign. If one current entering the dot, your dot, and leaving the dot, then it will be negative sign, right. So this is, everything is written here for you. Now if you, that is, this one we wrote in time domain. Now if we want that it will be your frequency domain, the reactance, mutual reactance will be omega into m. L omega we have studied, so it will be j into omega m, and this is my your current I1, this is I2, and this is j omega L1, right, and this is your j omega L2. This is XL1, XL2, right. XL1 is omega L1, XL2 is omega L2, and Xm is equal to Wm, that is the mutual reactance, right. So here sometimes we write Xm is equal to omega m. This is your mutual reactance, and here this one is equal to your XL2 is equal to omega L2, and this one your XL1 is equal to omega reactance of coil 1, reactance of coil 2, and J is there because it is inductive coil, and this is J is there because it is inductive coil, and this is your mutual reactance, right. So this is in the frequency domain. Here we will solve all the problem in whatever little bit in frequency domain. So now this one, now because of this coil, because of this current, a mutual voltage will be induced in this. So in that case you can write this one I1, L1 is there, this is the inductor, this is L1, or you can write if it is reactance, you can put omega L1, j omega L1, this is also you can write j omega L2, this is the reactance of coil 1, and because of that a voltage will induce it. So it will be j omega I2 plus minus and j omega, because of this current I2 a voltage will induce, and this is your mutual inductance was m. So it will be j omega m plus minus, and it will be j omega m your what you call I1. Now question is, just hold on, let me, so this is understandable, right. Instead of L1 I make reactance, and this current I, so voltage is here, easily you can find out what will be the current, right. So just let me clear it. So here this, in this equation also, in this equation also same thing you will get. What you will do is, just remember at this stage, you d dt you replace by your j omega. If you replace d by dt, this d by dt j omega, then you will find this will become j omega L1 I1 plus your m j omega m I2, right. You replace d by dt by j omega in this equation, you will get the same thing, right. So according to that, in the your what you call in that your frequency domain, the polarity of that induced voltage in other coil is taken. If you put here, if you put your d by dt you replace by your j omega, this right, then this one will become L1 j omega into I1. That means basically it will become j omega L1 I1. Here also it will become j omega m I2, right. So that means this is your what you call, this equation is written. Now then I1 you can easily write, I1 is equal to then V1 divided by j omega L1 plus j omega m, your what you call you can write this equation, your V1 is equal to your j omega L1 plus j omega m I2, right. So I mean if you write equations here, later we will see how to solve it. For example, if you write V1 is equal to here j omega L1, right, then I1, and this is an induced voltage due to the mutual coupling, this voltage source is added here. So plus your j omega m your I2, right, is equal to V1, a KVL, you put KVL here, you are applying KVL here, right. Later we will see how to solve it, we will take some problem, we will solve it, right. So mutual inductance as voltage generators. So this way you can replace in frequency domain, it is written here mutual inductance as your voltage generator, as if it is generating some voltage, right. So now two coils are in series. If two coils are in series, how it looks like? Look, in this case only how to write the equation. In this case that current I is, they can see series, two coils are there. Look here, in the, take this first coil is dot, current is entering into the dot. In the second coil also same current I is entering into the dot. That means sign should be plus. This is L1, L2, their inductances. So here I1 entering into the dot of, this is one coil, is dot is marked here. So current is entering into the dot, and this is another coil whose dot is entering, marked here. So current actually entering into the dot of the first coil, same current I entering the dot of the your second coil. So sign should be plus, right. So that's why first if you write the V is equal to, it will be L1 di, and then mutual inductance between them is M, right. So V is equal to L1 di upon dt plus M di dt, because current is same, it is a series circuit. So current is same, right, plus L2 di to dt plus M di by dt, because two coils are there. So repetition will be there in the series circuit, twice it will come. Once, because of when you are writing your for this coil, it will that M di dt will come for this coil because of this coil, and for M di dt will come here because of this coil. So repetition will be there, right. This should not, one should not make any error for this. That's why twice it is there. You have to, as if you are considering each coil independently, right, and that's why twice it is there. So once, because of this coil same current is flowing, voltage will be induced here in M into di by dt. Similarly, because of this coil that current I is flowing, a voltage will be induced in just this coil M di by dt. So that's why twice it has come. So V is equal to L1 plus L2 plus 2 M di by dt. This is the time domain circuit, right. Same thing will happen. Suppose another thing can happen. So let me clear it. Same thing. Suppose dot is not here. Suppose I put the dot here of this coil. So in that case, what will happen? The current I actually entering into this dot, but the same I leaving the dot, right. This is not there. This dot, this is not there. Suppose dot is here. You have made the dot. So current entering in one coil, but other coil current leave the dot. So in that case, sign of this one should be plus, sign of this one should be minus. It will be minus, right. It will be minus then. Sorry, not this one. Here it should, let me clear it. That sign of this one will be minus, and sign of this one will be minus. If you put, instead of dot here, if you put dot, because here current is entering and current is leaving. That means in that case, general, instead of plus it will be minus. It will be minus then N1 plus L2 minus 2M. In general actually this should have been L1 plus L2 plus minus 2M, because if you put the dot here, if current leaves this thing. Similarly if it happens that this dot is here and this dot is not there and this dot is here. So in that case, what will happen? Current actually leaving the dot, right, but in this coil current entering the dot, again it will be minus, again it will be minus, again it will be minus, right. So that means your what you call this one sign, when once it is entering, another is leaving, it will be minus. Now similarly, if you take another one, suppose dot is here and dot is here, this dot is not there, this dot is not there. So here also current leaving the dot, here also current leaving the dot, current, both the coils current leaving the dot. In that case, the sign should be plus, right. Sorry, not this one, sign should be plus, this one and this one, the sign should be plus. So that's why if both the current leaves both the dot or enters both the dot, plus sign. If the current either of this coil, once it is entering the dot, another is leaving the dot, it will be minus sign, right. So this is time domain. Now if you come to your frequency domain, so mutual inductance will be j omega m, and this is j omega L1, j omega L2, right. So now because of this, like your what you call, that is a circuit with mutual inductance voltage generator. I told you twice it will be repeated, right. So j omega L1 j omega m I and j omega L2 j omega m I, right. So this is I told you it will be repeated. So this way you can represent the circuit in the frequency domain. So that means if you now try to find out I, then if you now apply KVL here, so basically then it will be j omega L1 into I1 j omega m j omega I. This will be your voltage source. It will be, I mean writing for you. So if you make it here, it will be j omega L1 into I, then this is plus j omega m I, right, plus j omega L2 your I, right, and then plus j omega m, right, omega m I is equal to V, right. So, you can find out what is I, right. So, because this is as if this is a voltage source j omega m I and this is j omega m I, right. So, that is why it is an inductance voltage generator. This way you have to conceive it, right. So, that is why what I have written here, right. This is what I have written here. So, ultimately it will become I is equal to V upon j omega L1 plus L2 plus 2m, right. If it is the way we have taken, and all versions I have showed you how to take it, right. If the dot on one coil reverse, the sign of the mutual your term either in equation 2 or in equation 3 will be minus. I explain everything to you. That means the equivalent inductance of the two mutually coupled coils connected in series, it will be L1 plus L2 plus minus 2m, right. I mean, if you just one of the coil, if you just change its position, right. So, it will be L1 plus L2 minus 2m, right. So, that means in general it will be L1 plus L2 plus minus 2m, right. Since the net inductance must be positive, so it will be L1 plus L2 greater than equal to 2m. This is equation 6, right. It has to be greater than equal to 2m. Now, when two coils are in parallel, suppose these two coils are in parallel, that is series. Now, this is a parallel. What we have done it here, that current is this cyclic current is taken I1 and I2. So, in the direction of this one, it is I1 minus I2. It is marked here, and here the current is cyclic. So, this is current is I2. That means I1 minus I2 entering into the dot, I2 the current I2 also entering into the dot, right. So, when and this is in time, this is what you call, and this is actually frequency domain. That means this is 2 dot and this is the mutual reactance j omega m, it is written here. This is j omega L1 and this is actually j omega L2, rest are same, right. So, as the two currents are entering into the dot, I1 minus I2 entering into the, because this direction is I1 and this direction is I2, we have taken the resultant in this direction. So, I1 minus I2, right. So, I1 minus I2 entering into the dot, I2 also entering into the dot. So, that means this way we will go for your dot convention, means when you write the equation plus sign will come, and this is the mutual inductance M. So, if you write like this, this is this equation. So, like your that is same way we are putting that mutual inductance voltage generator in frequency domain, we are writing it. So, I1 minus I2 is flowing j omega L1, this will be j omega m I2, right. So, plus will be plus minus will be there, because both I1 I2 entering the dot, I1 I2 are entering the dot. That means along with your this drop, it will be additive, right. Little bit be careful about this. If I change the dot from here to here L2, suppose after top, if I put the bottom, then polarity here will change, right. You have to be careful about that. So, similarly here also, due to this I1 minus I2, voltage will be induced here. So, j omega m into I1 minus I2, right. So, you now what you do is, there two meshes are there. So, what you can do is, you try to find out what will be V upon I1, what will be your V upon your I1, right. So, here you apply KVL, here you apply KVL and solve for I1 and I2. So, I am giving you the final solution, so some time will be saved, right. So, in this case, if you solve it, it will be your what you call, it will be actually small I1. Here it is capital I1, actually it should have been by mistake I have a capital N, V upon I1. If you solve it, it will be your j omega into L1 L2 minus, solve for your j dq, V upon I1. If you solve it, it will be j omega L1 L2 minus m square divided by L1 plus L2 minus 2m. I suggest you please derive this from the previous circuit. That means from here you please derive this from here, right. You derive this from here. You apply KVL and solve it for V by I1. So, it is small I1, right, a small I1, you will get this. Now, look at that, whether m is negative or positive, m square will be always positive, right, and it is L1 plus L2 minus 2m. So, equivalent inductance will be L1 L2 minus m square divided by L1 plus L2 minus 2m, right, in this circuit. The sign of m in the denominator of equation 8, this it changes with the dot polarity, but the numerator does not change, since m is your what you call m square is positive. That means, if you put the dot, if you interchange the dot, right, then sign will change, sign of m will change, right. That means, this equation, it may become plus also, this the denominator, right. So, whatever dot we have taken, according to that become minus. If you interchange the dot and solve it, it will become plus, right. That means this your m is negative or positive, it will be here, it will change, but here m square is always positive, right. So, that is what is written here, right. So, equation 6 we have established that L1 plus L2 greater than equal to 2m, that means m, and here for since overall inductance, that is for series circuit, we have seen series circuit L1 plus L2 greater than equal to 2m, and the overall inductance must be positive if L1 minus your L1 L2 minus m square greater than 0, right. Here we have established that L1 plus L2 greater than 2m, that is always positive. Here also for making positive L1 minus L2 L1 L2 minus m square greater than 0, greater than equal to 0, or m less than, from this equation m less than equal to L1 plus L2 by 2, and from this equation m less than or equal to root over your L1 L2, right. So, this is arithmetic mean and this is geometric mean, right. So, geometric mean is always less than arithmetic mean, that means this value, this is the so this is the value we have to taken. For example, suppose you have a two number, say 3 and 5, its arithmetic mean is 3 by 5 by 2 is equal to 4, right. But if you take it geometric mean, it is 3 into 5, it will be root 15, right. So, this is geometric mean, it is less than your what you call less than 4. So, geometric mean is less than the arithmetic mean, except they are equal. If you take both are same 4 4, then both will be same, right. So, that means equation 10 states that the mutual inductance must be less than the arithmetic mean of L1 and L2, while equation 11 states that mutual inductance must be less than the geometric mean of L1 and L2, but geometric mean of L1 L2 less than the arithmetic mean of L1 L2 if they are not equal. For example, that means root over L1 L2 your less than equal to L1 plus L2 divided by 2, right. So, if L1 I mean it will be equal only when L1 is equal to L2, otherwise it is less than, right. So, therefore, the maximum value of mutual inductance can be taken as m max is equal to root over L1 plus L2, but not L1 plus L2 by 2, right. Therefore, from equation 11 we define that we get m by root over L1 upon L2 is less than equal to 1. This is equation 13. Therefore, we define k is equal to, say this term k is equal to m by root over L1 L2. This is called coupling coefficient and k lying between 0 and 1, right. Physical meaning of K1 is that all the flux produced by the current in one of the coil links the other, right. So, if it is k is equal to 1, iron core transformer k is approximately equal to 1, and air core coils k much less than equal to 1, that is very small, right. So, with that, thank you very much, we will be back again.